So you want to go ahead and get started?
Are you ready to go?
I'm ready.
Okay. It looks like there's no more people coming in.
Okay. Thank you.
Hey, good afternoon, everyone. My name is Gaiman Yi. I'm the Technical Director of the i4energy Center. And welcome again to everyone to another of our Friday seminars. Also want to say welcome to those that are viewing the seminar on the web. Today's speaker is Lloyd Cibulka. He is a research coordinator at CIEE. He has over 34 years of experience in the electricity industry. At CIEE, he is a member of the Electric Grid Research Group, where he develops and manages research projects in transmission system infrastructure and renewable integration for the California Energy Commission's PEER program. Previously, Lloyd worked for PG&E in the R&D department and the transmission planning department. He has a BS in EE from Washington University in St. Louis and an MS in EE from the Georgia Institute of Technology. Let's welcome Lloyd.
Thank you. Okay, can everybody hear me okay? Good, thanks. Thanks for coming. Title of my talk is Synchrophasors and how they're making the grid smarter. I guess you've all heard about smart grid, and as Gaiman said, I'm a transmission guy. I used to work in transmission for PG&E. Transmission is the high voltage system, and I'll show you some pictures later and some description. But basically, us transmission engineers, we get a little bit miffed when people start talking about the grid being dumb and it needs to be smart. We already know the grid is smart. It's smart in a lot of ways you don't see, in a lot of ways that it really is sophisticated. But you just don't see it, and given the trends in today's electric industry, the grid needs to get smarter. So first off, just a brief note on CIEE. I see a lot of my compatriots here, and I'm going to give a shout out or two to them as we go through this thing. But basically, we're a research management group composed of a bunch of experts, so to speak, in the various technologies. I'm transmission. I work, excuse me, for Dr. Merwin Brown, who's our program director, and these other folks who work with me are also experts in their own right, and we work in electric grid research. CIEE also has these other groups, energy use, behavior, climate change, carbon sequestration, planning evaluation, and enabling technologies. Our good buddy Gaiman Yi is the director of the Enabling Technologies program. So at the end of this, I'll have some links, including a link to the CIEE website, which is a brand spanking new website that we just put a lot of effort into. We're quite proud of. And so I encourage you to go to that site and look into all the great things we're doing. Peruse our mug shots, which all got new pictures up there. So anyway, there's a lot of stuff that we're involved in and a lot of experts who can answer questions if you have any in those areas. I want to give just a brief shout out to California Energy Commission's Public Interest Energy Research Program. They've underwritten a lot of the research that we've done at CIEE, and a lot of what I've learned about synchrophasors and other transmission technologies in the last few years has been due to working on some of the projects they funded. And we've also got a big project on adaptive relaying using synchrophasors funded by the DOE. And so we're going to talk about that later. So this is basically the outline of my talk. I just want to give some background, tell you what synchrophasors are, how good they are, what they're good for, where things are in the industry right now with getting them into the grid, and some of the research activities that are going on. First off, a couple comments on the smart grid. One thing you learn when you dig into this is that smart grid means different things to different people. It also means different things whether you're talking about transmission or whether you're talking about distribution. So for those that aren't really familiar with the differentiation of the electric system, transmission has evolved over a 100-year period to deliver bulk power, high amounts of power, usually from remote large power plants at higher voltages, usually 60 kV and up, 60,000 volts and up. It's highly networked, highly meshed, and with a lot of automatic controls, advanced protection systems, and real-time monitoring and control, and a lot of other great attributes. Distribution is usually at lower levels of power and voltage, usually under 30 kV or so. Power goes shorter distances, and it's mostly a one-way flow from the transmission system through a step-down bank to the distribution. We'll have some pictures later to give you an idea what this looks like. But it's a much simpler system. It's made that way for reliability, for low cost, and for reliability to the customer. And there's I won't say very little, there's not much in the way of real-time monitoring on distribution systems. This is one of the problems with distribution and why, in the view of, admittedly, a transmission snob, that the distribution system needs to get a lot smarter, a lot faster than the transmission system does to handle the challenges coming toward us. And so for that reason, I say that smart grid technologies will be different between transmission and distribution. And just for the record, again, my whole talk is pretty much from a transmission perspective. I'll talk a little bit about distribution at the end. And as it turns out, we do have one expert in the audience who is probably much more conversant with some of the monitoring possibilities and instrumentation advancements in distribution. So if a question like that comes up, maybe I might defer to that person. And just for the record, that's Alex McEachern right here with Power Standards Lab. Okay, moving on. Again, I want to go through a few of these slides just to give you the flavor of what transmission looks like. If you've ever seen a map of the Western grid or the US grid, that's what these are. All these lines are transmission lines. And so what you see is a big mesh or a net. That's what we talk about when we talk about a grid. On the Western system, a little bit more of a close-up. Here you see, here's Nevada, here's California. All these lines are high voltage transmission lines. These lines here, these are high voltage DC lines as opposed to, they're direct current lines as opposed to alternating current lines. And as it turns out, when you're transferring large amounts of power long distances without the need to drop the voltage down and serve customers en route, then you like to go DC because it's cheaper, it's more compact line. But it's only usually for distances over several hundred miles. The rest of the time you have what are called overhead AC transmission lines. That's what these guys are. 3 phases. Here on this one, these are actually what they call double circuit tower lines. You have 3 phases on one side, that's one line, 3 phases on another side, that's another line. And over here, you have the same thing, except you can even see the bundled conductors. In other words, for each phase, there's actually 2 or more conductors to provide more power transfer capability. So this is a system that's really set up to deliver lots of power over relatively long distances, but also provide a lot of flexibility in terms of being able to drop the voltage down where needed to lower voltage networks to serve customers, because the vast majority of customers are on lower voltages. This is a substation, as we call it. This is a node in the system. This is where transmission lines all come together. You have transformers, protection equipment, control equipment, switches, capacitors, inductors, all kinds of gizmos that the transmission system uses to control and manage its power. Now, the distribution system, by contrast, is a much simpler system, and it's what we call normally, in most cases, it's a radial system. That is, whoops, go back. Can't get the hang of this thing. The laser thing's in the wrong place. Anyway, up in this area, and again, here's a shout out to our colleague, Professor Alexandra von Meyer, who's in the audience. She had a really good presentation she put together called a tutorial, which she gave at Berkeley here last July, June, sometime. Really good tutorial, top-down explanation of the grid, the electric system, how it works, and lots of pictures. This one basically shows a radial distribution system starting up in here. Let's see if my pointer is a little bit brighter. Yeah, a little bit better. So I'm going to use this one. Maybe a two-fisted speaker here today. So the transmission system is up here. The bulk power is taken off of a step-down bank, probably a 230 to 60 kV or 21 kV bank, something like that. And then you have what are called feeders. These are these radial circuits, primary feeders that go out into the neighborhoods and the subdivisions and the office parks and drop down power to the customers, these little green dots. So you see the power flows from transmission out, down to the customer, usually one way. That's how distribution has evolved. That's how it mostly is. Now there are some radial, or what we call networked distribution. Downtown San Francisco is a good example where they put in a networked feeder system to provide higher reliability and power transfer to the downtown office buildings in San Francisco. And there you get into more of a transmission mentality in how you design and operate the system with protection, reconfiguration, and so on. You have multi-directional load flow depending on the conditions and so on. But that's fairly rare. There are some, but mostly distribution when you're serving the customers, it's radial like this. And here's a distribution line. There's actually a 138 or 115 probably kV subtransmission line at the top on these three insulators. Down below you have a primary distribution, 12 to 21 kV. And then right here you have a little single phase step-down bank that is a single phase drop down to customers. And so here's a close-up of this kind of transformer showing the primary inputs where you take the power off of between two of the phases on the primary distribution and then drop it down to a lower voltage, and now you have single phase to the customer. So one of the challenges, real big challenges in the power business is because we have so much single phase customer load in this country, that's just how we do it, is to keep the phases balanced load-wise. This is very important from a transmission and distribution operation viewpoint. You want to keep the loading and the currents and the voltages on the three phases as equal as possible wherever you can to reduce harmonics, imbalances, overheating of components, and so on and so forth. So that's a big balancing act that the utilities go through. Now now I'm going to segue just so give you an overview of the system. Again, we're talking mostly about transmission, but phasers and synchrophasors, they're a measurement technology. And what they are is a phaser is basically just a measured quantity. I should have put the word measured in there. Such as voltage or current that varies as a sine wave. So this could be, say, the voltage at a bus or the current at a bus. Doesn't really matter. It's a phaser. It's a sine wave with a frequency of 60 cycles per second. So one cycle would be right there. That's 0.01667 seconds, 1/60th of a second. Another way to represent a phaser is as rotating vectors. Apologize for the gunk in the diagram there. That's an artifact, I think, of my Excel chart. But this is another way to show phasers. Visualize these vectors as rotating counterclockwise, like the hands of a clock, at 3,600 RPM, 60 times a second. But phasers 1 and 2 will always stay the same separation from each other, and they will also stay the same separation from a reference. In this case, I'm showing the GPS reference, which is what synchrophasors are synced to. But basically, these kinds of sine waves have always been measured in the power system, usually with analog equipment, with a certain amount of accuracy. Measurements are used for regular instrumentation, such as system protection, where the current and voltage measurements are monitored by the protection equipment. If they get out of bounds disastrously, then the protection system will operate circuit breakers, and I got some pictures later on. I just hope there's enough time for all this. I think I threw too much in this presentation. Now, basically, so if you know what a phaser is, and what's a synchrophaser? A synchrophaser is just a phaser that has been time-stamped to an extremely precise and accurate time reference, for example, a GPS clock. And in the power system, this is what we use. We use GPS. So now, the advantage of this is that you know very, very accurately the angular separation between these phasers. You know very, very accurately their magnitude in real time. Analog instrumentation is usually kind of slow. And for a lot of the operational purposes, it's just not fast enough to be able to correlate all the variables from around the system to be able to do wide-scale or full system analysis. So that'll become clear as we go through some of the applications. So any questions on this? I mean, it's a very simple concept, really. Basically, what you do is, here's the Western system. This donut, as it's called, is the Western Electricity Coordinating Council, collection of utilities all interconnected by this high-voltage system. And the WEC, as it's called, is what's called a reliability council, where all the members work together to ensure the integrity and reliability of the grid. They cooperate on system studies and collaborative studies to make sure that the power can get swapped around and sent where needed, and so on. But these phasor measurement units, as they're called, are being employed in more and more substations to provide this synchrophasor measuring point. The analog data from the current transformers and voltage transformers is taken into this GPS, into what's called the phasor measurement unit. Oh, and from now on, every time I say phasor, just think synchrophasor, because that's what I mean. I mean, it's just, and we talk about PMUs as phasor measurement units, which is what they do, but then they add the timestamp from the GPS satellite. Then that time synchronized data goes into a central place. It can be a computation center, a control center. It can be the WEC office in Salt Lake City. It can be anywhere. But now, all the data that comes in is time synchronized down to like a microsecond. The PMUs basically sample the analog signal once a cycle, so that's 60 times a second. So everything you're measuring, it's got 60 measurements a second on that variable, accurately time-stamped so you can correlate it with any other measurement around the system in virtual real time. I say virtual real time because you're going to have some latency in the telemetry transmission, the computation, and so on, but you're still talking milliseconds, not months, to do a correlation kind of study. So the data comes in, it's time synchronous data. It goes into various applications, visual displays, basically ending up as, I say, virtual real-time information, but it's pretty darn close to real time. And this is a very powerful and enabling capability for this, for system operators and planners to have this kind of information, and particularly to be able to visualize in real time what the system is doing, what things might be going wrong, what things might look funny to look out for, and then when things do go wrong, they can look at the system and analyze much better what to do about it. So this is kind of the whole concept of what we call wide area monitoring systems, or WAMs. That's what this is. We're taking data over this wide area. It's all time synchronized. We've got a real-time snapshot of the system. Before synchrophasors, you couldn't do this. You could do something, you could simulate this, but it would take you months at least to pull together all the data, correlate it well enough to do this. Now you can do it in real time. That's the beauty of this. So we show here how with a traditional, I took the animation out of this because it's too tricky, but with traditional real-time data rate, with conventional, monitors and sensors, you're only taking a snapshot of the system like every 4 to 5 seconds. And again, it's not time synchronized. It's just data. You have to pull that data together to do anything with it. Now we've got it 60 times a second. And this is basically just an unprecedented ability to see, know, plan, and control the power system in real time. So what are the application areas of synchrophasors, the key ones? These 7 areas are what we go by. It came out of a report that the CEC sponsored we did a couple of years ago called the Phasor Measurement Application Study. This was done by KEMA, a fellow there named Damir Novosel, who's now with Quanta Technology. And Quanta Technology is probably one of the leaders in how to use this synchrophasor information in advanced applications. They do a lot of work with industry in this area. This was a very pivotal study. And so what we came up with is, first and foremost, it really Synchrophasors really enable real-time monitoring and control. It has improvements that are just too many to mention in terms of being able to operate the system in real time and enable the operators to do things they couldn't otherwise do. State estimation, I'll talk about that. That's a way of using data to estimate data that you can't measure directly, and that's helpful. Real-time congestion management. In California, we had a problem with transmission lines getting to their limit, and they're called being congested. You can't put any more power down them, but that also limits a path. It also limits the parallel lines that the power is trying to flow down. So how do you deal with that? And in real time, you can do a lot of things with synchrophasors. Post-disturbance analysis. A lot of what we're doing in synchrophasors has come out of post-disturbance analysis of some blackouts, which I'll get into in a minute. But basically, once a big blackout happens, it typically would take months, if not longer, for engineers to go back and gather all the data about what happened, try to figure out what went wrong, what the sequence of events was, what failed first and what made something else fail. So they could put together a list of lessons learned, things to fix, mitigation measures, so on. And that's really what that's all about. With synchrophasors, you've got this data already. It's already collected electronically. And so you can probably cut your post-disturbance analysis time by a factor of 10, if not more, by using the synchrophaser data that's now available. There's also benchmarking and system model validation. An awful lot of what the power industry currently uses and depends on, the kind of tools they depend on for doing system analysis are based on models. They model the system in the computer. They do a lot of what-if contingencies, test the limits, and come up with operating limits and constraints and guidelines as to how to operate the system. But that's only as good as your models are. If your models are no good, or if the data is inaccurate, you're going to come up with erroneous results. So synchrophaser data is just, much better garbage in to get much better garbage out, so to speak. Power system restoration is being able to put the system back together after a blackout. When the system falls apart, it islands, breaks up into pieces. How do you put it back together? You've really got to work on getting your phase angles right, your voltages right, matching generation and load at the same time, bringing everything back up. Very tricky business. And real-time data from synchrophasors will be very helpful in this arena. Then there's adaptive protection. I talked about protection systems. You guys know what circuit breakers are? Well, in the power system, there's circuit breakers, and there's a lot of other stuff, too. There's wide area remedial schemes, special protection schemes, things that are based on wide area data that are more than just monitoring one line and a short circuit and opening a line. So there's a lot of benefits from adaptive protection, particularly in avoiding blackouts, which I'll get into in a minute. Okay. So real-time monitoring and control, I talked about this. One thing you'd like to do is monitor phase angles in the system. I'll have a picture later on where it shows the phase angles of a system in terms of colors, where from one end of the system they're diverging from the other area of the system. And you have to keep an eye on this because this is an indication of the stability of your system. The farther apart the phase angles go, the more stress on the system, the more likely something will break. And so the operators would really like to have that kind of information. We're getting this problem on the Western system now called low-frequency oscillations. This is a new manifestation of something we in the transmission business used to call small signal stability. In other words, we're finding out that the power system starts to oscillate. In other words, instead of being steady and not moving, the frequency starts to vary, the voltages and currents and power flows start to vary, and nobody knows why, and they can't control it. So the only thing the operators can do now is just basically back off the power flows, take some of the stress off the system until it calms down. But by doing that, that's an uneconomic way to operate the power system. It's usually more costly, and you're leaving a lot of unused capacity on the table. Synchrophasors have some promise in being able to not only detect what's going on, but where the problem areas are, and in the future, possibly be as input to a control system where you might have some storage or some other controllable devices on the system that you can put some power pulses into or out of those systems to counteract the oscillations and have an active control system. And that'll be informed with synchrophaser data. And then voltage stability. The voltage is a big problem on the system. When things are heavily loaded, the voltage gets depressed for a number of reasons, and it gets uneven, and in certain areas it can actually be deficient. And when things start to go downhill voltage-wise, it's sort of self-reinforcing, which is bad, so you really want to stay on top of that. Okay. This is just a picture of something we call the real-time dynamic monitoring system. We did some research on this with some funding from Peer, and this tool, as it's called, is now in use up at the California ISO. So this just sort of gives a screen with some information, and the operator can click on things and find out what's going on with various things in the system. Basically, it's a way to visualize and keep track of the dynamics of the system through real-time monitoring with, of course, synchrophaser data being the thing that enables this. Here's another kind of busy slide. I just want to point out here that this kind of diagram is, if you think back to that rotating phasor diagram I had, here you've got angles, you know, red, yellow, green. This is a way of keeping track of the angular separation in the system. Okay, so you can, if some angle separations get too big, you're saying this generator is pulling away from the system and it's going to go unstable. So this gives you early warning. And I will mention that anecdotally, we've already been documenting success stories at the Cal ISO where they've averted what they think could have been very bad events by having these kinds of visual tools available to them so they could spot problems before they get really bad. And they never had that kind of observability or visibility in the system before. State estimation is, I mentioned, a way of estimating data that you can't measure directly or you don't have a monitoring point directly in your system. But you still need that information to calculate power flows or voltage or whatever. So state estimation is just a numerical analysis method that takes the data you do have in your system model and says, okay, here's my best estimate of the data you don't have. And that works fairly well, but it could work so much better with synchrophasors. Much more data, more redundant, more accurate, more precise, and in real time. So all this stuff not only could be done better, it can be done faster. So contingency analysis is just looking at your system and saying, right now I'm fine, okay? But what happens if this line goes out? It's gone out before. What if it trips? What happens? You can run a quick study and it'll say, oh, this is what happens right now, this instant, if that line goes out. If that's a bad thing, do something to inoculate yourself against that. Constrained generation redispatch. The Cal ISO, does a generation dispatch every day, every hour to keep the generation in balance with the load. If a generator goes out, now they got to redispatch under the constraint. They don't have that other generator. There might be other path flow limitations and so on. And so this allows them to do that very quickly. Volt-VAR optimization, again, is just actively managing the voltage profiles on the system to keep everything on an even keel. And congestion management is where you have a transmission line. In California, I don't have the graph up, but between, say, PG&E and Southern California, there's a major path called Path 15, which is a collection of transmission lines all feeding power down the intertie, as we call it, the Pacific High Voltage Intertie, to Southern California. That path can get constrained in the sense that one of the lines in that path will get to its loading limit. Now you can't put any more power down that path, even though some of the other lines still have capacity on them. So that's called congestion, and that's expensive and it's hard to manage. With synchrophasors, you can look at the conditions in real time, maybe adjust your path limits, do some real-time rating of those conductors in those lines, and find a way to get more power down, even in the face of apparent congestion. So I talked about congestion management just now, and there's benefits of that are huge. Not too long after Cal ISO started running the California system in 1998, they found a lot of congestion in the system, and at one point it was costing almost $1 billion a year in extra costs. What they have to do in congestion is you have to back off certain generators that are feeding power into that congestion and pay them not to generate because they put the least cost bid in the market and they have a right to generate, but the congestion says they can't, so they have to back off and they get paid for not generating. Conversely, another generator on the system has to bring their generation up, and a lot of times they'll say, well, you know, man, I don't want to generate, you know. Unless you want to pay me more money, I'll generate. And so then the Cal ISO has to pay that generator more money to generate while he's paying somebody else not to generate. So that all costs lots and lots of dollars. Well, in the meantime, we've fixed some of the constraints here, and so now it's not quite as bad, but it's still several $100 million a year in congestion costs on the system. Post-disturbance analysis, I already kind of briefly talked about that, but basically what you want to do is figure out what went wrong after a blackout, figure it out fast, get some fixes in place, and learn from it. And with synchrophaser data, that's going to be a lot easier thing to do. It's still hard, but it's going to be easier. Benchmarking and model validation, I already talked about that too a little bit. I want to kind of scoot through these because there's some better stuff later on. But basically, PMU data allows you to do a much better job in identifying errors in your system modeling data. So in other words, you have better models. And when you do your analysis studies, you come up with better, more accurate results that correspond more to real life. And there's a lot of benefit in that. You can't do everything in real time, but you can do much better estimation of things on a simulation basis. And this is a slide I like to use to show what bad models do for you. This was the August 10th, 1996 Western blackout. It started up in the Northwest somewhere, you know, a line got hot, touched a tree limb, relayed out. That touched off a series of events. But basically what happened is after a while, the system started to go unstable. You got these power swings that just were what we call undamped. Normally in a system, in a sine wave system, you have what's called attenuation. Your, you know, e to the minus alpha coefficient, or what do you call that? Subscript or superscript. Yeah. So anyway, in this case, instead of these oscillations dying out due to just friction and damping in the system, they're growing, which says this is a problem. The system's in a stressed, unstable state where a disturbance is causing it to go unstable. Now, after this happened, they went back and they actually took the existing system data at the time, put it into their simulation studies, and simulated everything that went wrong. They could not reproduce this oscillation with modeling studies. The model was no good. And this model is what system operators and planners use to run the system. And so they're saying, we got to fix that. So this is why good models are better than bad models. And power system restoration, I already talked about this. Basically, but you want a more accurate post-event scenario, simplify and speed the restoration process, and minimize the length of outages seen by customers and the resulting cost to all parties. The whole concept of cost of outages is a very tricky one. What's your outage cost you? If you're a business, you can come up with some numbers. But there's a lot of stuff that's not quantifiable. But everybody agrees that having your service go out when you don't want it to is not a good thing. And so utilities do try to minimize that. Okay, I'm going to talk about protection systems a little bit because this is this DOE project I was talking about that we're doing in adaptive protection. But protection is basically starts with circuit breakers. That's these little boxes here. A circuit breaker will protect a transformer, it'll protect a line, it'll protect a generator, based on whatever you're trying to protect. Like with a generator, if it starts to overspeed or underspeed too much or over torque, you want to trip it off. But also, if the transformer gets overloaded, you want to trip it off. That's what these circuit breakers are designed to do. They're designed to just basically be automatic switches that open up, separate the equipment from the system so that it doesn't get damaged or the system doesn't get damaged. There's a big circuit breaker. These are 3 single-phase circuit breakers. So what I showed you before was what's called a single-line diagram. It only shows one phase of a 3-phase system. And that's for simplicity, because all 3 phases are supposed to be balanced, so it's all the same. But in real life, this is a an oil tank circuit breaker. You can see the little spigot at the bottom where you can drain it. Modern circuit breakers use gas, SF6, as the insulating medium. And so they call them gas insulated breakers, or that's normally what you buy these days. But these are the devices that actually interrupt the power. The full load current is going through this thing, and these switches in here basically open up. They get signals from the relays, as they're called. The relays used to be electromechanical devices that were basically fancy solenoids. You'd put your current transformer would take a small percentage of the load current, put it through the relay, and at normal times the relay would just sit there and say, fine, nothing's going wrong. But as the current got to elevated levels, the solenoid disc would start to move, and eventually it would short some contacts, which would send the signal to the breaker to open. This is not unlike a starter relay on a Ford car, for example. But the relay used to work on a time over current electromechanical principle. Now, they're just little computers. This is a little rack mount, or could be a rack mount relay from Schweitzer Engineering Laboratories. They were one of the first to do digital relays. And the capabilities of this are immense, way more than most protection systems will ever use. But the system is very cost effective, very reliable. I can remember visiting Washington State University back in the 80s when I was on a campus recruiting trip for PG&E, and I actually talked to Dr. Schweitzer, who was teaching there at the time. And he said, you know, we got this, me and my buddy, Jakanowski was his last name. We're working on this digital relay. I think PG&E might be interested. And I said, I don't know. I'll take information back and see what they say. And I went back and talked to one of the relay engineers I work with on system studies, and he said, yeah, we're interested in that. He says, we know we got to start moving to this stuff eventually, and I'm glad somebody's working on it. So this is back around 79, 80, and that's when these things first started being developed. And there were relay engineers and actually power system engineers at the time that said, I don't want my system being run by a computer. I don't trust them. You can't take the operator out of the equation. Well, these things have pretty much supplanted electromechanical relays on the transmission system. And computers, I think, are, you know, they run probably 95% of the system, and the operator usually steps in when something's going wrong. But there's so much automatic control now, it's just not, it's not believable. And that's all been happening in 30 years. So anyway, the relay is the device that takes the original current, voltage, signal, whatever, does some computations, and tells the circuit breaker when to trip. So what's adaptive protection? Well, adaptive protection is where, in normal times, your relaying is set for all lines in service, normal conditions, everything fine, everything healthy, and you set it for certain conditions, certain levels of fault current, certain levels of voltage, under frequency, so on and so forth. When things go wrong, lines go out, generators go out, you know, loads go on and off the system, you're basically hoping that that relay is still seeing more or less the things it should be seeing and will operate more or less the way it should operate. However, as we're finding out in a lot of this post-disturbance analysis from blackouts, is that relays do not operate correctly in all cases, particularly when the system is highly stressed, when there are multiple outages leading to a cascading outage. And it's been documented, not only in this 96 blackout, but also in the 2003, 2004 blackouts of more recent vintage, that relays were operating, tripping out lines, tripping out generators, when analysis showed you'd rather they didn't do that. But they had no way of knowing, they had no way of adapting to the conditions. So what we're doing is demonstrating on a PG&E Southern Cal Edison transmission line how to do adaptive relaying. And basically, adaptive relaying, I call this a description because there's a lot of different kinds of relaying systems, a lot of different ways they need to adapt to conditions. The one I'm going to tell you about is just one example. But adaptive protection is something that the protection engineers would really like to see happen because it'll have a lot of benefits. There's a lot of different ways to look at this. There's backup zone supervision. I'll talk about that in a minute. Intelligent load shedding. That's another thing that happens during blackouts. You have a line go out, something is overloaded, or there's a generator has to trip off. Now you've got a generator load imbalance. Now you're tripping load, but you trip a certain block of load, and it's too much. And now you got to drop a generator, and then that's too much. Then you got to drop load. You know, it's just not very smart. So we want to do that better. Loss of field relaying is a generator-specific thing. The field is the excitation in the armature that provides the magnetic field for the generator to provide power. And sometimes it loses its field energization, and it's hard to detect. But also, it'll do that under different conditions, so you want to be able to adapt to those different conditions. I talked about the oscillation damping controller, these big, slow oscillations on the system. You want to be able to detect those and do something about them. Adaptive reclosing, this gets into the restoration after a fault. If you have more accurate information about phase angles, voltages, and currents in the remaining system, you can match things up better and put the pieces back together quicker. And fault location. When a transmission line, particularly a long one, has a short circuit and relays and goes out, it's because there's something wrong with that line that needs to be fixed. And if you have a 40, 50, 60-mile long line, where do you start looking? Well, you start at one end, and you get in a truck, and you drive to the other end. How long does that take? It takes a while. But now that you've got all these fancy schmancy digital monitoring techniques in real time that record their data, you've got it all at your fingertips, all you have to do is go into the data set and say, where the heck is the fault? And the algorithm will go and say, okay, based on the fault currents and the harmonics and all the things we looked at, it's between towers X and Y in so-and-so county at this exit off this freeway. So the guys go right there and they fix it. And that's one way it's a lot smarter and easier for the maintenance guys. This, again, is a cascading outage. This is the Malin to Round Mountain flow. That's the line between Bonneville Power Administration and PG&E, or one of them. And this just shows that there's a lot of things that happen between the inception of the cascading outage and when things finally go down the tubes. And here, at this point, is at 1542, the Kiefer-Alston line tripped. And as you see, you know, there was some oscillations. And basically, I think the post-disturbance analysis showed that this line didn't need to trip. But because it did, it made the system weaker. Then something else happened here. It's not marked, but you see the ringing. And what's happening is the damping, which is measured in percent, is getting less. 3% is bad. I mean, it's getting very low. And it should not have rung like that. I mean, that signal should not ring like that. And things keep happening all along here until finally something happens, and that's all. It's over. The system can't take anymore. Straw that broke the camel's back right there. So this is why wide area monitoring is good. Now, the project that we're doing, it's called Application of Advanced Wide Area Early Warning Systems with Adaptive Protection. But basically, we're going to be demonstrating three things. How to adapt the relaying system for security dependability. That basically means how does it detect stress systems and how does it supervise the relay characteristics so that it doesn't trip when it doesn't need to. The second is relay zone encroachment detection. And this is more not when something happens in real time, but as things evolve over time. As the system has more lines and generators put in or loads move around, more loads come on, more renewables. The relay characteristics should shift with that evolving scheme, but it doesn't. And so this just gives operators and protection engineers visual ways of seeing what's happening so they can say, maybe I need to go out and readjust that relay setting. I don't need to do it in real time, but I can do it, you know, in weeks or months. And then we're doing some visualization work with something called a protection information tool, which is a way of visualizing the impedance or the protection information. And we're doing this on an actual line. This is sort of a schematic of how it works. We have the Midway to Vincent 500 kV line. PG&E owns Midway, SCE owns Vincent. They both have operating control centers that have protection laboratories, as they're called. They actually have protection system control centers that run all the special protection schemes for the Western, for our part of the Western grid. These are things that take in wide area data, look at the health of the entire grid. They don't just look at individual lines. But the PMU data that we're monitoring in the field comes in, goes into these system state and impedance calculations, and it does two things. The information goes out to what's called a voting algorithm. On this transmission line, as it's similar for a lot of 500 kV high voltage lines that are very critical tie lines between companies, we have redundant relaying systems. There's actually 3 of them. So this is not just belt and suspenders, it's also safety pins holding your pants to your shirt. Because, you know, if your belt fails, your suspenders hold them up, and if that fails, then safety pins are the last. Anyway. So they do this because it's very, very important that if there is a fault, that it be detected and the line tripped out before something happens. So this is one way of ensuring a very high degree of dependability, i.e., the fault is cleared when there really is a fault, okay, by having redundant relays. Now the problem becomes that any one of these relays can trip the line. The other 2 may not see it, but one does. And if one does, and all lines are in service and there's no stress in the system, you can survive a trip of one line. The system is designed to be able to tolerate a trip of a single line with everything else being fine. That's the extra margin that's always been built into the system. Again, for reliability and dependability. It's redundancy. However, when the system is stressed, in other words, lines out of service, things are happening that are sort of the impending signs of a blackout, then the relays have a much higher probability of tripping falsely. And then if they do that, they contribute to a blackout. So what the PMU data does and what the algorithm that's in here does is it detects when the system is in this stress state by bringing in all this wide area data. And when that happens, and it detects those conditions, it sends a signal over here and says, institute this voting algorithm now. And it puts it in place. And what the voting algorithm says, it says, I want 2 out of 3 relays to say trip. And otherwise, don't trip. If it's just one relay, it's probably a false trip. And if you look at the probabilities of that, it's very, very high probability that that'll work correctly. So the voting algorithm then comes into play during blackout conditions, and it prevents the relay from tripping falsely and contributing to a blackout. Now, the encroachment data comes into this protection information tool, and I'll show you that in a minute. But here's where the key PMUs are on the system. We've got Vaca-Dixon, which is just north of here off of 80. This is Tesla, which is that big substation right off of 580 out past Tracy. There's Diablo Canyon, and there's Devers, which is a big major substation in Southern California. Those are the PMUs. Those 4 sets of PMU data are sufficient to feed into this algorithm and have the algorithm say, okay, I know when the system is stressed and when it isn't. This is the relay, impedance relay zone encroachment. If you can see this, the zones on a relay, each relay has a primary zone and a backup zone. The primary zone, what that says is, if the fault is closest to this relay, it should trip first, instantly, fast. If it doesn't, if it fails somehow, then relays that are farther away, after a little bit more time, will then trip and clear that fault. So it's backup protection. Now the problem with these zones is they're fairly big, and this is basically a resistance versus impedance or inductance plot. This is the zone of the relay. And normal conditions all have, these essentially is the impedance, system impedance seen by that relay, looking back into the system from its vantage point. Normal conditions are out here and out here. Give me plus flow, minus flow. That's what this represents. But if something happens and there's say there's a fault on the system and the system oscillates, you can have an operating point here, swing into here and back out. And when it swings into here, if it gets into here, that relay is going to trip. So what you want to do is keep tabs on this and look at these voltage excursions or these load excursions. And when they start getting close to this thing, then you want to think about doing a relaying study and reset your relays. The visualization, this is being done by Mississippi State University. The 2 the two adaptive relaying algorithms, the Midway-Vincent algorithm and the load encroachment algorithm, are being done by Virginia Tech, who got a lot of experience in this area. Basically, I'm not going to go into this too much, but visualization of data is very important for operators as well as planners. I mean, it's one thing to look at tables of data, but if you can translate that data into graphs, pictures, things that make cognitive sense, you can find your way to solutions a lot faster if you're a planner or an offline engineer. Here's a possible, I don't know how clear this is. This is an oscillation damping and alarm visualization proposed scheme. Over here, this particular line says if you're getting out into this area, your damping of your system is getting very low. That's very bad. So if your operating system is here, you're close to an alert threshold, which is 5% damping. Over here, this is nice. This is close to 20%, so that's a very, very good damping spot. But this is just a way to say, okay, here's your operating condition. Are you close to the yellow threshold or the red? And it's an indication you need to go and do something in your system to get out of that area. Because otherwise, if another line relays or something like that, you're going to go over into there and then it's all over. So this is a way to visualize that. This is that bus angle visualization I was telling you about. Over in here, you've got the dark orange represents an angle of 20 degrees on whatever reference scale you're using. As you go this way, the angles get lower, which is to be expected. I mean, angles have to vary across the system because power flows from high angle to low angle. That's how, on a first approximation basis, that's how it works. Voltages go more on differences. I mean, VARs, which is the imaginary or the reactive part of the power, flows more as a difference in voltages. So that's why voltages, VARs don't travel very far in the system. That's why you need lots of local voltage control all over the system, because you want your voltage profile to be flat. It does not allow VARs to travel. Probably doesn't make a lot of sense, but it does to us transmission guys. Anyway, if you get all the way out here, up in the northwest, this looks like Massachusetts versus, well, this is St. Louis right here, or right here. So this is 20 degrees, and all the way out here is minus 140. So the angles, the voltage angle here and the voltage angle here, are almost diametrically opposite. They're not very close together at all, which could be good, could be bad. I mean, it's all a question of, in your experience, what angular differences portend disaster and which ones portend, good conditions. Okay. I don't know why I threw this in here. I don't even understand this. But this is what one of the things Mississippi State is working on is because the data is electronic and it can be used for a number of different things. I had a slide I wanted to show the time frames of the different applications. Some are really fast and others are slower, but it was a bad resolution slide, so I didn't put it in. But basically, there's layers of communications, protocols, and services for sensor data. It goes to automatic controls, it can go to visualization, it can go to offline studies, it can go to other control centers. There's all kinds of communication protocols and standards and all kinds of stuff. And this is supposed to visualize that. I can't explain it to you, but I threw it in there. I thought it looked kind of cool. We'll talk about the regulatory entities. FERC is Federal Energy Regulatory Commission. They have permitting or regulate interstate transmission electricity, among other things. NERC, which used to be the North American Electric Reliability Commission, sort of a voluntary agency. It's now the enforcement arm of FERC. So they enforce reliability standards. They're the ones that are really big on this, what's called the North American Synchrophaser Initiative, or NASP. They and DOE are basically pushing NASP as the means by which utilities and everybody else all get on the same page on how to use synchrophasers and work out the protocols and everything else. I'll talk about DOE activities. There's the Smart Grid Investment Grant, which basically gave a lot of money. It's part of the stimulus program. Gave a lot of money to utilities and other people to actually put in synchrophasers and other infrastructure to lay the groundwork for some of these advanced applications. And then the Smart Grid Research Program, which funds R&D projects. And that's what our adaptive relaying is one of those. These are the projects. I won't go through them. If you're a transmission wonk, you probably recognize some of this. But there's a lot of research going on, and this is just the tip of the iceberg. A lot of people are doing stuff outside of this program on smart grid kind of activities on transmission. Okay, what about distribution? Well, currently PMUs and PDCs are expensive. They haven't been used on distribution system much, but there's growing interest in doing that, what with trying to figure out the effects of EVs, renewables, and everything on distribution feeders. And some of this is just my opinion, but I think in the near term, some potential first applications might be just looking at key feeders, say for power quality applications, for premium service, or to see the impacts of EVs, if they're clustered on a feeder, things like that. But I say research is in the embryonic stage. Alex, you may disagree with that, but I think we're just starting to figure out what we might want to do there. Synchrophasors are rapidly moved from R&D into applications. But even in raw form, the data is good. It helps you. Utilities are deploying more and more, and pretty soon they'll know what to do with all the data they got. Applications and benefits have to catch up and make use of the data that's out there. But the technology is cost effective, and with micro synchrophasors, it'll be cost effective for distribution monitoring, hopefully someday. And I think that's pretty much it. This is for more information. I put some websites here for you to look at. Where's ours? There's ours. And when you go to our website, go to the tab Research and go to Electric Grid, and that's where our stuff is. But there's a lot of other good stuff on here. This one I just found. I think it comes from DOE or somebody, but there's a lot of good stuff on there. And with that, I'll finish. Thank you.
Thanks. Thank you, Lloyd.
Right on time.
So
Okay.
we'll open the floor for questions.
And I'm willing to stay after if anybody has time.
I see your hand over there.
I didn't think I was going to fit all that in 1 hour.
Who owns the grid? Does the grid belong to one person or one company, or who owns it?
Okay, the grid itself, the physical assets are owned by a combination of private power companies like PG&E, San Diego Gas and Electric, Southern Cal Edison. They own the lines. They own the actual physical equipment. There are also public utilities, like SMUD is one, Santa Clara, Modesto Irrigation District. They're public. The private companies are owned by shareholders, people that own shares in the company. So it's basically a whole bunch of people that own it. In the public utility, the people that live in that geographic area own that system, and it's operated as a local government entity. Then there's regulatory agencies like the California Public Utilities Commission that regulate what utilities can do, what lines they can build, so on. The California ISO operates it. So the grid is owned by a bunch of different people with different governmental standing and different capital standing. So it's a very complex system. But one thing I will point out, since you talked about ownership, how about the question, who owns the synchrophaser data? Okay, so if a utility is monitoring stuff in its territory, it has PMU data that it has collected. However, it can't just give that data to anybody. The FERC-NERC people under NASP say the interconnected grid is being operated for the benefit of everybody. And one utility, they've taken some synchrophaser data, but that data essentially belongs to the whole grid. And FERC and NERC have responsibility for the whole grid. So they say that utilities have to sign what's called an industry non-disclosure agreement that describes how to handle that data, who they can give it to under what conditions, so that that data is protected, that it's confidential, and so on. Because other companies, even if they're on the other side of the country, they have a stake in the safe operation of the grid. What PG&E does over here with that data affects public service, electric and gas in New Jersey to some extent. And so FERC has expanded their ownership of the data to say, we say how it should be used. And there's good reasons for sharing data, and other people can see your data, like operators in neighboring utilities would like to see some key points in your system So they're apprised of problems or line outages or whatever in your system that might affect them. And that lack of awareness of that kind of thing is another major contributing factor to blackouts. It happened in the Northeast and it happens in the others. Operators would always say, well, if I knew so-and-so line went out over there, I'd get on the phone to that operator and tell them, drop to Cincinnati. You know, save your system. But they didn't do it. Next thing you know, Cincinnati goes down, and then Ohio goes down, and so on and so forth. So, but anyway, yeah, the grid is owned by a bunch of different people. And actually, distribution systems are sometimes owned by different entities. PG&E, for example, and Southern Cal Ed have transmission and distribution, but there are a lot of distribution-only companies that buy wholesale from the transmission and then resell. I mean, Alameda County is a public utility that kind of does that, and others do that too. So it's a pretty complicated ownership issue.
So I have a quick and specific question here.
Okay, hi.
So if you go beyond monitoring applications of synchrophasors to control applications where actual decision makers take action, and the broad sort of objective is to get more out of the existing infrastructure,
Right.
set relay protection a little softer and so on. Is there the concern that everybody's own actions, you know, uncoordinated, are going to send the system a lot more towards instability? Who coordinates? You know, if I look at your synchrophasor data and then I change my sort of algorithm for my protection equipment, you know, whose responsibility is it? Are people worrying about it? Are people doing validation, verification studies, etc.?
The way I would answer that is to say that in the West, I mean, I didn't have a graph of the whole United States with all the different coordinating councils. But there's WEC in the West, WCC. There's Midwest ISO. There's the PJM in the East and the EIPP, I think, in the Northeast.
How do they do it?
These are all reliability councils. And historically what they've done, and synchrophasors don't really change the basic mechanism, but what they've historically done is they said, look, all us interconnected companies in this region, we have an interest in common standards, doing common studies, to make sure that if somebody wants to up the flow on this path over here, it's not upsetting the other side of the grid. So they do, the WECC has their own staff, and they have people in the utilities that belong to them that also are on working groups that do all these studies, and they coordinate, and they meet, and they decide whether it's safe to do that. It's a collective, collaborative process. And so it's not going to be any different with synchrophasors. It might be better, actually, but in the past it was always a slow, laborious process. You did your studies, you went to the WCC, and you said, here's what I want to do, and the other guys got to critique it.
I'm talking about real-time issues. You know, if in real time I do this and do that, it might send the system towards an edge. So, you know, is there a real-time mechanism to coordinate this?
Well, I think that goes into the planning studies. Nothing will be done in real time unless somebody is able to simulate it with the standard studies and with the standard models and say, I've tested this scheme or this operating behavior or this contingency, whatever, this relaying scheme. We've tested it all together, and we all agree it's okay to do it. And so they will have the studies that shows what happens under all these things. Nobody will be taking an action that hasn't been studied. So that's how it's done.
With all this improved visibility of the grid, do you think we'll ever move in the direction of moving from the current approach of protecting the equipment at any cost to a paradigm where the tripping decisions would balance the cost to the public versus the cost of the equipment on a stochastic probabilistic basis?
I don't think so. I mean, you know, there's a valid reason for protecting the equipment. And usually if there's a local problem with, say, a generator or a circuit breaker, again, there's so much redundancy in the system that you should be able to trip any one thing unexpectedly and the rest of the system be fine. Again, there's usually loads and loads of planning studies that go into this kind of thing that say, okay, here's this generator over here. If it just trips off for whatever reason to protect itself, and to save whoever owns that generator millions of dollars in repairs, it should be able to do that, and the grid should be fine. Okay, so I really don't see a case where you would not want to do that, because if there's a problem with the equipment, you either trip it off or it's going to fail and trip anyway, and the impact on the grid and the customer is going to be the same. So what you need to do is look at the overall scheme and take that into account and have enough redundancy and enough reserve margin in the system that it can handle that. So again, I don't know that I can visualize a scenario in which equipment would have to stay on and burn itself up in order to save the public. I just don't see that happening.
When you had the big blackout in San Francisco in '96, was, I mean, much of the blackout was because you went into overgeneration, undergeneration, so you took a sequence of relays.
Right.
If you were less conservative, probably you could have avoided it, but nobody puts any cost on disrupting the whole city for 8 hours. So therefore, you are always favoring the taking decision on putting all the risk on the consumers and putting all the
Well,
safety on the equipment.
Well, here's what you got to keep in mind. The electric grid is the world's largest and most complicated machine. Okay, it's got zillions of moving parts, and it's operating in real time. Has to keep everything in balance within very tight limits. You got to maintain 60 hertz, or these big generators blow up. It's that simple. They don't tolerate lots of swings, and so if a generator starts to speed up, you either drop it and save it, or you let it go and burn up and lose it.
You don't need 0.035 hertz deviation protection. You can go to minus a plus a hertz and still the system will fall. It's the tripper is the
Well,
tripping that causes the blackout. It's not the fact that we cannot tolerate that kind of deviation.
Well, I disagree. I think it is the fact that you can't tolerate those kinds of variation, that the relaying is designed the way it is.
Plus minus 2 hertz.
No.
I'm not
Uh,
sure,
that's-
maybe customers' equipment may start going bad if,
Given the fact that the bulk of the generation on the system comes from large rotating fossil fuel machines that have to run at a very specific frequency, they don't tolerate lots of off-frequency operation. The mechanical torques are killer. They will blow the machine up, they'll snap the shaft. That's just the reality. That's how you get big amounts of power very cheaply, is through these big rotating machines. Now, if that power came from, say, a solid-state source like a huge battery, it wouldn't be an issue at all. But it's the nature of these machines that it is the issue. Okay, so, well,
Okay.
that's
We'll
a
have a-
judgment call that I can't make because I don't study those machines. But
Well, I might like to try to restate Shmuel's point and
Mm-hmm.
say, in a way, this is sort of testament to how little empirical observation we have, because I think there is, it's fair to say there's some range of uncertainty of what fraction of a hertz is going to cause physical damage to the synchronous generator, right?
Mm-hmm.
So there is a little bit of slack where you do make an engineering judgment and say we're going to set this under frequency relay to a point where we're going to be pretty sure that the generator is not going to get fried.
Right.
But we don't have a lot of empirical data to say, well, if we went down by another, 100th of a hertz, by another 200ths of a hertz, where does the damage actually start? We don't
Right.
know that. And so it's the business of, navigating this terrain where you don't really know. And historically, we have the culture of wanting to play it safe because we know that if we err on the wrong side, then it's going to take a really long time to fix and get through it.
right. Now, one other thought on that is that when we get into these scenarios, these blackout scenarios where you're dropping generation because you've got too much and then you drop load because there's too much, usually by the time this happens, you've lost a bunch of lines and other things have tripped. And the point I tried to make earlier is that a lot of those lines that trip don't need to trip. And that's what puts you in this situation where now you're just trying to avoid catastrophe. You don't have a full healthy system. If you did, and these lines were in, there probably would be much less of a threat to these generators, and you would have fewer instances where you're dropping them to save them, and you'd have fewer blackouts. I mean, that's why, we're hopeful that through adaptive protection and some other kinds of advanced applications that are coming along with synchrophasors, we actually will be able to avoid some of these big blackouts.
Point that a lot of this extra safety is because we don't have precise measurements, and the more
exactly
precise
right.
measurement you have, you can be a little more push the limit a little, the boundary a little more.
And I don't think even transmission engineers would argue with you if you said, you know, we're in a bad state and this line is overloaded and it's running hot, but don't trip it out. Let it go ahead and run hot. I mean, that's a component we can tolerate some abuse of. And even if it burns down and melts or whatever, we can put another conductor up and it's a lot less money than a new generator. So lines, we're very, very conservative on protecting lines. And as one who's done a lot of looking at real-time rating of transmission lines, there's an awful lot we can do there to get more capability and realistic capability out of transmission lines. Whereas today, we operate them just as conservatively as we operate the generators. And there's no reason for that. That's true. Sure.
In terms of matching the generation frequency with the grid frequency, what are there aspects related to energy efficiency that should be considered? In other words, how much energy are we dissipating by not having a perfect match between the generation and the grid?
Well, under normal conditions, everything in the grid is operating at exactly 60 hertz. There is no difference in electrical frequency. The generators, of course, all have their rotating mechanical frequency, and depending on how many poles the generator has, they could either be running at 3,600 RPM, or they could be running at 1,800 RPM, and they could be running slower. Hydro machines usually are multi-pole and run a lot slower. But electrical frequency in the system is maintained at exactly 60 hertz, everywhere, for everything. Unless things start to bounce around, in which case they move. But you always want it back to 60 hertz. You can't have one generator operating at 59 hertz. It just doesn't work.
We're talking about tolerance before, right?
Yeah.
So I think this gentleman was saying you were running at...
No, the tolerance is that when you have like a frequency dip like that, because it will happen.
Right.
Whether you trip the generator or trip the load or in order to avoid that.
Yeah. Yeah, so it's a dynamic thing. And what happens when you start operating a generator off the 60 hertz is you start introducing lots of torques, armature overheating, bearing wear, shaking, vibration. A lot of stuff can happen.
Well, and the point to clarify is that when that frequency deviates, it deviates for every generator on the system. So the question is not, are we going to try this one, but all generators.
And let's make a distinction, you know, that there is the generator frequency as it's varying during a fault. That can go plus or minus maybe several hertz, but it'll always come back to 60. What's worrisome is when the system frequency starts dropping. I mean, the frequency of the system overall, that means you've got a major mismatch between generation and load. If there's not enough generation, the frequency is going to start to fall as the machines get loaded and slow down. And the opposite happens if you've got less load than generation on the system, the machines will start to speed up. Now, I don't know really what a given synchronous machine's tolerance would be for a steady state operating frequency, but I can tell you that like for a steam turbine, it's not so much the generator part, it's the turbine part. The blades, a huge mechanical rotating mass with blades, and it has, you know, it'll have resonances at off nominal frequencies and vibrations and all kinds of stuff. So it's very finely tuned to operate optimally at 60 hertz. And operating at a steady state frequency off of that is not good, but I don't know what the limits are. I really don't.
Well, there's another way of looking at it. If you're off the frequency that you need to grid. Another way of looking at that is if you're just changing phase angle constantly with respect to the anchor.
Right.
So you become a motor after you've done 100 degrees out of phase.
Right, and actually there was that one graph I showed where the power started going like this. I've done many, many studies at PG&E when a generator, you know, looking at the generator and how it responds to a fault. You know, you look at its frequency and it starts at 60 and it does something like this and settles back. You look at its power output, it starts here, starts bouncing around and settles at a new power and so on. But when the generator slips a pole, as we call it, when it gets out of synchronism with the grid, there's nothing you can do except trip it off and bring it back later. You can't bring it back. And what you see is you see the voltage do this and then just start going like this as it constantly slips poles with the system. Yeah.
Yeah.
Sure.
You talked about the low noise oscillation and
low frequency.
low
oscillation.
frequency, I guess. My question is, what is the problem with putting all this renewable in when you're going from battery or storage and using an inverter, to which usually has a lot of harmonics and transients, and how are you catching that? And is that usually done on the distribution side or the transmission side, I guess? And I'm wondering how, where you are, at what percentage renewables you can handle without having, unstable grid. I think that's more important than talking about a generator rotating.
I can't answer that question definitively. All I can do is wave my arms and talk around it quite a bit. But basically, the low frequency oscillation is a characteristic of the huge interconnected grid. And nobody knows exactly why the grid is oscillating on its own, what we call small signal stability. In other words, a tiny little switching operation somewhere creates a little energy, and all of a sudden the thing starts sloshing around. I mean, it'd be like if you were in a supersonic plane and a bug hit your windshield and all of a sudden you start oscillating. It shouldn't do that, but it does. It means you're operating the system somehow too close to the stability limit. But you don't know why, you don't know how much margin you have, and you don't know what's causing it, but you can see the oscillations, okay? And so what they do is they just back off the transfer flows around the system to reduce some stress, and usually the problem goes away. But this is being studied very intensively right now for causes and mitigation methods. Now, the whole question of renewables is something, again, we don't know what's going to happen. We're going to have to learn as we go. So far, I don't think, the problems with renewables on the system has been ones of capacity. In other words, they want to connect in places where there's not enough transmission or not enough capacity on the existing transmission. And so the question is, who pays for the transmission? Okay, so there's that. But there's also the operating characteristics, the intermittency, the variability, the fast ramp up and ramp down, and that's going to need solutions like better forecasting of wind and solar, maybe some storage as a grid management device that can counter these ramps. Basically, with ramping of renewables, like say you have a big wind farm, all of a sudden the wind comes up and they ramp up. What that means is you've now got to take down other generation on your system to balance with the load. And sometimes there's so much wind in certain places you can't use it all, in which case you have to spill it or you have to try to pay people to take it or whatever. So there's that issue. But I think what we're really worried more about is the ongoing variability in the output of these plants and how that's going to be managed on the grid to keep things within proper boundaries. And that's an evolving area of research and discussion. Well, see, that's the thing with the transmission system. I mean, an electric system in general. The public sees, voltage at 60 hertz coming out of their socket. They use it all the time. When it's not there, they throw a fit. Okay, fine, that's great. But what I'm saying is, if you were to look at that power 100 years ago from that same perspective of the user, it doesn't look any different. But yet the system back there has been improved and upgraded and expanded immensely. We're putting in improvements all the time to keep up with trends just to maintain the standards we have now, to maintain that reliability. So there's so much stuff going on behind the scene you don't even see, just to keep up. So what could we do in the system that would actually make the customer stand up and give notice? I mean, what could the power coming out of the socket do for the customer that would be any better than it is now? What we have to do is maintain the reliability and make the case that the system continually needs to be upgraded to keep up with trends and pressures on it. And that's kind of a tough sell sometimes.
Well, thank you, Lloyd. Thank you
all
for
Thanks,
coming
everybody.
today. And I hope no one came because thinking this was a Star Trek convention.